Welcome, everyone, and thank you for joining us for today's webinar. My name is Dan Abir, and I will be hosting the webinar today. Our webinar's title is Optimizing Data Center Design and Performance, and will be presented by Perry Lee from TotalSim US. In today's webinar, we will cover the following topics: key challenges in data center thermal management and how they can be resolved, explore how proper thermal management can ensure optimal performance, generating efficient cooling for data center reliability, performance, and reducing energy consumption. We also are going to include some collateral and links that you thought you might be interesting called Improving Data Center Cooling and 11 Top Tips for Energy Efficient Data Center Design and Operation. The collateral will be made available as a link in the chat section of the webinar control panel for you to download and review after the webinar. Just a little housekeeping before we get started. This webinar will be recorded and made available upon request or in a follow-up email to attendees. Your microphone and video will be muted during the presentation. If you have any questions during the webinar, please type them into the question box in the control panel in the question pane, and we'll address your questions after the presentations are completed. You can also look for updates and links to resources in the chat window, as I mentioned. And of course, don't forget to download them after the event is done. TotalSim was founded in 2009 with a sister company in the UK. We are based in Dublin, Ohio, with the technical center in California, and have about 10 engineers with CFD, aerodynamics, and physical testing experience in a variety of industries, including aerospace, automotive, renewable energy, and more. We have three primary ways we help people move quickly from concept to reality by leveraging our capabilities in engineering, prototyping, and test services and software. We can help create and improve conceptual design through design analysis and optimization processes. We can create a digital twin, a physical prototype, and test it and correlate the results by simulating, prototyping, and testing the physical model. And of course, we can train and mentor your team in proper use applications and help automation of your CFD software if you wish to bring it in-house. In addition to proprietary engineering software that TotalSim develops, we also partner with Siemens, which offers the most comprehensive portfolio of tools needed to bring Industry 4.0 to life and make the digital enterprise a reality. Before we jump into the work we have done in this area, I wanted to briefly review some of the critical issues impacting data center design and performance. As you know, data centers are critical infrastructures that power modern computing, but also create significant design and operation challenges due to increasing power densities, heat generation, and energy consumption. Increasing power density and heat generation problems that impact the grid, energy bills, and such. These key issues and their implications are at the heart of our webinar today. Since traditional air cooling is increasingly adequate, advanced solutions like liquid cooling, AI-driven optimization, and sustainable designs offer promising paths forward. For the sake of the webinar, we have explored some of these scenarios using CFD and multi-physics simulations and engineering acumen to propose some solutions and potential ways to optimize designs and layouts. We have to demonstrate the benefits of using CFD to create better designs, ensuring reliability, efficiency, and scalability moving forward. With this, I'd like to introduce our presenter. Mr. Perry Lee is an aerodynamics engineer with a background in external aerodynamics, CFD, wind tunnel testing, and aerodynamic database development. He has 8+ years of experience performing a variety of CFD analyses on various applications, from fixed-wing aircraft to launch launch vehicles to complex multiphysics simulations. Perry received his bachelor's in aerospace engineering from Ohio State University, and when he's not simulating data centers, Perry enjoys international traveling and running. With that, I'd like to welcome Perry to unmute and begin his presentation.
Thank you, Dan, for the introduction. I wanted to start with a short introduction to CFD. So what is CFD? Computational fluid dynamics, or CFD, is essentially a virtual wind tunnel. It was initially used in aerospace and automotive industries to simulate the aircrafts at different altitudes and the vehicles in different conditions. But recently, CFD has been heavily used across many industries, including data center design. For data center design, we're taking the physical room and moving it into the virtual world and using physics and math to solve the fluid flow around the room so we can better understand it. It's basically equivalent to a digital twin of the actual physical room. It involves the process of taking three-dimensional or 3D geometry and building a mesh, which we call a volume of fluid, within the room, and solving a bunch of math on a high-performance supercomputer. So what's the barrier of entry into CFD? Getting that 3D geometry into the virtual world is probably going to be the hardest step. I know a lot of you in the data center design world use Revit. And for those of you that are unfamiliar, it is a computer-aided design or CAD software where you can build 3D models of your geometry. I've come across others using Siemens NX as well. Basically, any CAD software will have the ability to export geometry into the format we can use to prepare the model. Other than geometry, the most important information is your heat sources and air supply information. It is the room's heat loads for your equipment and airflow rates if the cabins are exhausted. Also, airflow rates and temperature for your air supply. If you are modeling environmental gains and losses, we will require some more information. What this means is we can model internal heat leaving the room and as well as external heat entering the room. For example, we can apply a solar load on the room to model the warmest day in the year at a given location. We also do have the capability to model acoustics, which means we can trace mechanical noise generated from the hardware across the room. So what can CFD data tell you? First and foremost, the most important thing is understanding your design. A lot of times your initial design calculation would make sense to you, but there are times where something doesn't perform the way you're expecting. CFD can predict how everything works in your design, how the cooling system is performing, and how the cool air from the cooling system is interacting with the warm airflow exhausted from the equipment. We can also see how the flow moves around the room and identify overcooled and undercooled regions within the room. There have been scenarios where a user wanted to test different types of cooling systems, and because of room constraints, use CFD to make a decision between the different types of cooling systems. Lastly, your what-if scenarios. Reliability is often one of the most important criteria when designing and constructing a data center. CFD can be used to predict temperatures and undercooled regions when one or a combination of cooling system fails. There isn't a right or wrong time to incorporate CFD into your design workflow. In early stages, we can use CFD to look at basic airflow around a room, so you can use that information to best place your equipment and cooling systems. Design optimization validation is often the most popular time to use CFD. This is when you have an initial design and want to see how it performs. It could be a perfect design or optimization is needed to mitigate undercooled or overcooled regions. This could be several iterations. We've had final design failed, the failure analysis, so we're back at the optimization stage and another failure analysis after improvements are done. Again, this could be several iterations. Post-build design analysis is something that It's not as common, but can be extremely helpful. You have a functional data center, but it is underperforming. CFD can be used to identify issues and offer design recommendations. I'm going to go through a sample model that have been modified from an actual customer model, which for that model, I do not have rights to talk about. This is a 1,500 square foot of floor space with two main cold air aisles, 4 rows of server equipment on the east side of the room, totaling 93% of the total heat, 4 rows of the electrical equipment on the west side of the room, totaling about 7% of the total heat. Overhead split units as the cooling systems for the design. This model was prepared and simulated in Siemens Star CCM Plus. Previously, I spoke about how CFD works. I take your 3D geometry file and build a volume of fluid within the room. This is that volume of fluid created for that model, but sliced up in the east to west direction and also from the north to south direction. It can be sliced from top to bottom, which I'll show next. These slices can show how the cooled airflow from the cooling system interacts with the warm airflow exhausted from the equipment. In these slices, the dark blue region shows temperature starting at 60 degrees up to 102 degrees when it is dark red. What this shows me is that the heat exhausted from the server cabinets is trapped in the northeast and southeast corners. The cooling system on the west side of the room does a pretty good job cooling the warm exhaust from the electrical equipment, while the east side of the room, especially corners, are undercooled. These are also slices, but sliced from top to bottom view, specifically above the finished ground at 4 feet on the left and 6 feet. What these show is temperatures at human height level, making sure temperatures would be comfortable for whomever walks into the room. These slices can predict temperatures when people are walking through the cold air aisles. This shows an animation of warm airflow exhausted from the electrical and server cabinets. We can see how the airflow from these cabinets moves across the room. Again, we can see the warm airflow from the top and bottom rows of the server cabinets trapped in their respective corners. And we can see the warm airflow coming off the electrical equipment on the west side, and the first few server cabinets on the left side of the are cooled from the cooling system on the north, south, and west walls. In this animation, we can see how the cooled airflow from the cooling system are moving through the room. The north and south units are creating an air curtain effect. This air curtain effect traps the cold airflow from the east and west side units on their respective sides. This means we have the same amount of airflow on both sides of the room, even though the amount of heat is vastly different. If we recall, we have roughly about 7% on the west side and 93% on the east side. CFD can generate hundreds of millions of points of data, which means I can track temperatures at any point within the room. This chart shows all the average inlet and outlet temperatures for the electrical and server cabinets. The electrical and server cabinets used in this model have a critical exhaust temperature of 100 degrees, which means the inlet temperatures for these equipment needs to be under 80 degrees. Like we saw on the previous page, we have 2 warm regions towards the northeast and southeast corner of the room. The temperatures in the first red box are the equipment closest to the wall on the north, and the second red box are the same 2 equipment on the south side, which are over the critical temperature. With warm air trapped in the north and southeast corners, one way we can optimize the design is to modify the north and south split units with bifurcated ducts. This would have a dedicated duct supplying cool airflow into these corners. Everything else remained the same in the model. All the heat load setup remained the same. Looking at the same slice setup as before, this GIF flips back and forth from the slices in the model and our baseline model. We can see the improvements in the north and southeast corners, decreasing average temperature in those areas by at least 10 degrees. But we may have made other areas worse. If you look in the middle of the room, which was previously well cooled, we can now be too warm. Looking at these top-down slices at human comfort levels, we can see we improve temperatures in these corners, but we're starting to get warm at other areas. This streamline animation shows something very similar to the slices 2 slides ago. The north and southeast corners are no longer undercooled, but the middle of the room is now starting to be undercooled. This animation shows exactly what happened. Modifying the north and south units with bifurcated ducts weakened the airflow blowing north and south, therefore removing that air current effect. With weakened north-south flow from the second and third cooling system units on each side are pulled towards the north or south unit, leaving the middle of the room without proper cooling. The red column shows inlet and outlet temperatures from this revised model, and the blue from the baseline model. We can see improved temperatures from the equipment that was previously at or above critical temperature. But we can also see now that most inlet and outlet temperatures are much warmer in this revised model. The last iteration in this optimization sequence, we looked at a completely different cooling system. Instead of overhead split units, we have installed computer room air conditioning or hvac units. An air duct was installed to connect the chimneys from the server cabinets to the returns of the hvac unit. All heat load setup remained the same. Looking at these slices again, we can see no hot spots within the room. All of the warm exhaust flow from the server cabinets is contained in the air duct, and warm exhaust flow from the electrical equipment is cooled by the hvac units. You can even say the entire room is overcooled. In this animation, we can see the warm exhaust from the server cabinets go directly into the air ducts that is connected to the returns of the hvac units. Warm exhaust flow from the electrical equipment is cooled from the cooled airflow from the hvac units. This shows how the cooled airflow from the hvac units are moving throughout the room. You can almost see the 2 cold aisles in front of the server cabinets are overcooled. Looking at the slices at 4 feet and 6 feet, anyone walking through the room will be comfortable. Looking at these temperature plots, green temperatures are from the hvac model, red is from the revised bifurcated duct model, and blue is our baseline. You can see from our hvac units, we are well under the critical temperature for all equipment. So what do we see? With CFD, we can see how the cold airflow from the cooling system interacts with the warm airflow exhausted from the equipment. We can identify overcooled and undercooled regions and quickly make modifications to design and then reanalyze. CFD can be used to compare different types of cooling system, as well as their placement and sizing. Reliability has often been a critical concern when designing and constructing a data center. What happens to the room and equipment if one or a combination of these hvac units fail? We can use CFD to simulate and predict temperature and airflow when these hvac units fail. We can simulate the failure of each unit or a combination of different units. We previously saw in these slices for the hvac model, the hvac baseline model, with all systems on, there were very little hotspots, if any at all. There are a few hotspots appearing when different units have failed, but most of the room is still well cooled. In this chart, even with different crack units failing, inlet temperatures for all equipment are still well below the critical temperature of 80 degrees. We can use CFD to identify hotspots or equipment or regions in a room above or near critical temperatures and make design modifications if needed. In this failure analysis, we saw all equipment temperatures are well below the critical temperature, even though the failed cooling system units. So what does this mean? This means the room is well overcooled. Running an overcooled room could be costly. We can use CFD to optimize the cooling system efficiently, whether it is decreasing the airflow supply rate or increasing the supply temperature, or even increasing the delta T, which is the temperature between the return temperature and the supply temperature. Anyways, this is at the end of my short presentation, how we can incorporate CFD within a data center design workflow.
Okay, now I'm unmuted. Thanks, Perry. As usual, it's always interesting to see what you come up with when you're not hiking. Before we jump into the Q&A, and I wanted to take an opportunity here to remind you, please type in any questions that you have into the question panel, and also check out the chat window to see the links that we have added for the Improving Data Center Cooling document and the 11 top tips for energy efficient data center design and operation. Before we jump into answering some of the questions we've received, we have two special offers that we'd like to extend to you. One of them is 10% off of an engineering consulting project. So if any of this has enticed you to explore the potential of using CFD as a way to address some of your current or potential challenges in your existing or new data centers, we'd love to offer you an incentive to jump in. Or if you would like to bring CFD in-house, then we have put together this new CFD user program, which includes an extended trial license, training, and mentoring as a way to help you ramp up and apply the tools and the training that you've learned to your specific project. We also want to extend an option of accessing HPC and GPU hardware that would allow you to benefit from accelerating the solution time and seeing how hardware can impact the results. One of the trends these days is taking advantage of better hardware to get results faster, to enable you to optimize faster and such. So that's definitely something worth considering. So with that, I'd like to go to the Q&A section. Once again, if you haven't entered a question, please feel free to enter one. Let's see, got a couple of questions here. First question sounds pretty reasonable. How quickly can we expect to get results once we start a project? And so I'm not sure if that's enough information, Perry, but can you try and answer that?
Yeah, I can. So it really depends. If this is a brand new baseline project, so from receiving the geometry CAD file to you receiving the results could be around 2 to 3 weeks. I think a lot of it depends on how clean or tidy the CAD file is. If I or someone here has to make a lot of modifications to that CAD file in order to create a model, it's going to add time to the project. So once the baseline is completed, if we're just looking at changing conditions, scenarios like supply temperature or airflow rates, then a couple of days, like somewhere between 2 to 4 days, we can get results back to you. But if I have to modify CAD to move, let's say, cooling systems or electrical equipment or server cabinets around, then we can add another day or two to that timeline.
Awesome. Thank you. We have another question here. This is actually a hardware question, so that's kind of cool. What is the performance cost benefit of using on-premises based hardware versus cloud hardware?
That's a good question. I think this is a very popular question. If you're using internal hardware, you're always limited to how many cores you run these models on. So, for example, for these typical data center models, I run 192 processors. And let's say if your internal hardware is only 48 processors, you could be looking at solve times for about 4 to 5 times more than what I would see. But for cloud computing, you can use as much processors as you wish, basically. So we'll have to look at scalability in terms of cost. But if you wanted something back within a couple hours, the cloud computing, I think most cloud computing has GPU-based GPU-based equipment, so you can see results back much quicker.
Yeah, I was going to add also is that depending on hardware, and I have no idea how much your specific system that you're using, Perry, costs, but hardware on-premise hardware can get expensive. So depending on if you're using it regularly or intermittently, that could also, I think, impact the the reason to pick one over the other. I have just if anybody else has any other questions, please join in. I do have one more question that came in, and if we don't hear anything else, this will be the last question. So, how long does it take to learn how to perform these types of simulations if you have never done this before?
So for data centers, I think it's very unique. In the CFD world, there are lots of different types of CFD software out there. Um, there are GUI based, which is you have a graphic user interface, and then there are some without GUI based, which is all command line. What's good about what I've used here, I use Star CCM Plus. It does actually have a graphical user interface, or what people usually call a GUI. So the buttons are there for you to click. There's everything is within that tree that Siemens uses. But let's say if it's command line, where everything is through the terminal, I think that's a much harder process to learn. But what Siemens done, I think it's quite easy. So I think looking at, if you've never done CFD before and you want to import one of these into a Star CCM Plus or a GUI based software, I don't think it'll take a lot of time. I think the first couple of times, the first maybe baseline run, the follow-up run, I could be someone at Total Sim or me who can guide you through it. And I think by the third or fourth time, you should be able to do this on your own.
Awesome. Thank you. So I'm checking. I don't see any other questions here. Just a reminder, whoever hasn't taken advantage of the links with the additional documentation, this is your chance. And with that, I wanted to say thank you to everyone. This is the contact information. If you have any questions, we'd love to answer them. And as I mentioned at the beginning, we will be making the recording available to the people who have attended and on demand to your friends. So if there's anybody who who might be interested, please let them know that this is a resource that's available. So with that, I'd like to say thank you. We're going to be ending our recording of the webinar now. I hope everybody has a good day. Thank you and good